Quick revision video on alcohols, and I'm looking at functional group, shape, classification and physical properties. And if you wouldn't mind, hit the like button, and if you haven't already subscribed, please do so. So we'll start with functional group and shape. Alcohols contain the hydroxyl or OH functional group. That's not a hydroxide, that's a common mistake that I see. Shapes and angles in alcohols. So we've got this alcohol here, that's prop 2N1-ol. So we've actually got three different angles and shapes in that molecule. So we'll start with these two carbons here. So remember, shapes determined by the number of electron regions around an atom and how the repulsion is. So around those blue carbon atoms, there are 3 electron regions. Remember, multiple bonds count as one region. They're all bonding regions, so we're going to have equal repulsion. So the shape is trigonal planar and the angle would be 120 degrees around those two carbons. If we move on to this red carbon now, you can see we've got 4 electron regions. They're all bonding regions, so we've got equal repulsion again, and the shape is tetrahedral and the angle is 109.5 degrees. The third atom we'll look at is this oxygen here. So around this oxygen we've got 4 electron regions. Remember, there's 2 lone pairs on this oxygen as well as these 2 bonding pairs. So we've got 2 bonding regions and 2 lone pairs. So the repulsion won't be equal now. And if you remember the order of repulsion, lone pair to lone pair repulsion, which we have got here, we've got 2 lone pairs, that's greater than lone pair to bonding pair, which again is greater than bonding pair to bonding pair. So the lone pair to lone pair repulsion is repelling more than anything else, and that's going to reduce the starting angle of 109.5 that you've got for 4 electron regions. It's going to go down by 5 degrees down to 104.5, and the shape is non-linear. So moving on to classification now. Alcohols can be classified as primary, secondary or tertiary, and that all depends on the number of carbon atoms or alkyl groups bonded directly to the OH carbon. So we'll start with this alcohol here, that's propan-1-ol. So if we focus on the OH carbon, you can see we've only got 1 carbon bonded directly, or 1 alkyl group bonded directly to that carbon, and so that's a primary alcohol. The next one is 4-methylhexane-2-ol. So again, we'll focus on that OH carbon. Now we've got 2 alkyl groups or 2 carbons directly bonded to that carbon. That's a secondary alcohol. And finally, we've got this one here. That's 2-methylpropan-2-ol. Focus on the OH carbon and you can see you've got 3 carbons or 3 alkyl groups directly bonded to this one. It's worth just saying on this slide that methanol is classed as a primary alcohol even though it's only got hydrogens bonded to the OH carbon. So if we move on to the physical properties of the alcohols now, we're going to start with boiling point. So we've got this graph here of alcohols and alkanes. You can see the number of carbons along the bottom, boiling point up the side there, and you can see that when the carbon atoms, the number of carbon atoms is small, there's a very big difference in the boiling point between the alcohol and the alkane. The alcohols always have a higher boiling point, but you can see that the gap narrows as the carbon chain gets longer. So we'll look at that now. So alcohols have got the higher boiling point than the corresponding alkanes due to the presence of hydrogen bonds between the OH groups. So more energy is needed to overcome the intermolecular forces between alcohol molecules compared to alkanes. So in alcohols you've got hydrogen bonds and induced dipole-dipole forces, whereas between the alkane molecules you've just got the induced dipole-dipole forces. So if we look at a couple of comparisons, we'll start with this one, ethanol versus ethane. So that's 2 carbons, so this one versus this one. You can see we've got a big difference in boiling point. So if we just draw up the alcohol, the ethanol molecule. So we've got relatively strong hydrogen bonds between the OH groups, but we've got much weaker induced dipole forces between the alkyl part, the carbon part. And then if we just look at the alkane, ethane, all we've got is just those very weak induced dipole forces. So this extra intermolecular force means that the boiling point is quite a bit higher. So if we move on to the alkane and alcohol with 9 carbons, so that's nonanol versus nonane, there's the corresponding diagram. We've still got those relatively strong hydrogen bonds between the OH part, but now the induced dipole forces are much stronger because we've got more electrons in the molecule. And of course, between the nonane molecules, we've got much stronger induced dipole forces than before. So we're saying that as the carbon chain gets longer, the number of electrons in the molecules increase, so the induced dipole forces get stronger between the molecules. And what that's doing is it's narrowing the gap in the boiling point because the influence of the hydrogen bonding is becoming less significant. Or you could flip that and say the influence of the induced dipole forces is becoming more significant. So if we move on to solubility now, we'll just start off by explaining what happens when alcohols dissolve. So for an alcohol to dissolve in water, the energy released when hydrogen bonds form between the alcohol and the water molecules, that's got to be able to overcome the intermolecular forces between the alcohol molecules. And just remember, we've got hydrogen bonds and induced dipole forces between the alcohol molecules. So we've got this table here from a data book showing the solubility of alcohols in 100 grams of water. So this is moles per 100 grams of water, 20 degrees C. So you can see that the first 3 alcohols, methanol, ethanol, propanol, they're all completely soluble. So an infinite number of moles of the alcohol can dissolve in water. So small alcohols are infinitely soluble in water. You can see that as the alcohols get longer or larger, they're becoming less soluble. So for this one, heptanol, only 0.0008 moles per 100 grams of water can dissolve. And that's got to be down to the increasing induced dipole forces between the alcohol molecules. So again, just a couple of examples for comparison. So there's ethanol. So we've got 2 ethanol molecules and a water molecule here. So you can see we've got relatively weak intermolecular forces between the alcohol molecules, got the induced dipole forces between these parts, and we've got the hydrogen bonds between the OH groups. So when it's put in water, the energy released when these new hydrogen bonds form, that's obviously enough to overcome these intermolecular forces here. And so something like ethanol will completely dissolve. So if we move on to heptanol now, so the one at the bottom of the table, hardly dissolving at all. There's the diagram to compare. And now we've got much stronger intermolecular forces between the alcohol molecules, and it's down to this part of the molecule here because it's got more electrons in. So it's the induced dipole forces are getting stronger. And so when you put it into the water, the energy released from these hydrogen bonds forming is not enough to overcome these intermolecular forces between the alcohol molecules, and so it hardly dissolves.